Welcome to the last leg of the conference, but I'm super jazzed to be here, and I'm excited for all of you, and I'm really confident that at the end of this session, you will walk away learning two things. One, about Typeclass Induction, and two, about potentially using some of this stuff to do cool things with SQL. So stick around. Okay, so my name is Aaron Levin, and I work for SoundCloud. I run a team of machine learning engineers and data scientists. We work in search, recommendations, playback, genres, classification, all these fun topics. And what we're going to talk about today is something that I encountered at work in my day-to-day duties as an engineer before I was programming, or not programming people, but before I was serving people as their humble manager. And it kind of informed most of this talk. And at the end of it, I'm hoping you'll learn a little bit about how I solved this problem, but most importantly about this cool thing called Typeclass Induction, which is used in the ecosystem. And at the very least, you'll have a much more keen and a keen understanding of how typeclasses resolve in Scala and how you can use them to do cool things. So let's talk about what the problem was. So who here works for a company that emits data into a black hole? Where supposedly business value is accrued. Okay, so SoundCloud, people listen to music. The music is great. They keep on listening, and to improve our recommenders and improve the product, we emit events, right? So here are three classic events. There's many more. Click, play, pause. They'll be our friends throughout the rest of the presentation. And if you are a company that emits data and then collects it into some black hole where business value accrues, you're going to have some kind of architecture that looks vaguely like this, a big event sink. And then this stuff needs to go somewhere. So where the industry has consolidated around is a place called the data lake, where all the stuff ends up. And so if you're the unfortunate engineer who has to work on the event sink, well, you're going to end up with some kind of naive implementation of code in that area is going to do some kind of dynamic dispatching. So you're going to have some events. Here I represent them in a seal trait hierarchy, and then your code is going to be like, well, and you need to know how to parse these events, and because strings rule programs, and eventually your sink is going to be taking some kind of event name, some kind of payload, and it's going to parse it. And you're eventually just going to be like, did I get a click? Well, I'm going to parse it as a click. Did I get a play? Then I'm going to parse it as a play. So naively, you're going to have this kind of representation. And the problem that we had was that, we had something a lot nicer than this, but, we had this kind of stuff in our code, but then it turned out we had to use this list of sacred events in multiple places. So in our event sync, and then in our ETLs, and then in sticking it into the data warehouse, and everywhere around our code, we needed to know what was the list of events. And then a lot of the time, the code that we were using was if I know how to parse something, figure out how to parse one of these events, and then if not, fail. And after dealing with this and having to add an event and then update my code in 1,000 different places and deal with all these weird error cases, I thought I wonder if we can just somehow leverage type classes to accomplish this code so that it's a lot simpler. And so in the end, what the solution looked like, and I promise by the end of this talk you'll have a much clearer intuition for how this works, was I had my dynamic dispatcher, which was the thing you'll learn about in a second. And it would take a list of events. So here the list of events is click, play, pause, and I could use it to dispatch on an event, and it would give me a result. And this probably just looks like a bunch of nonsense right now, but you'll figure it out in a second. But what this meant is that I could have this canonical representation of my events: click, play, pause. And if I ever needed to add a new part or add a new event, I could use that representation to generate all my dynamic dispatching code wherever it was in our code base. Also, at the end of this horrible exercise in my life, I really had a strong appreciation for how implicits resolve and kind of the amazing things you can do with them. And so even if you don't necessarily want to, incur the debt that such a sophisticated machinery induces into your business accruing data lake, you doing this talk and talking about this process really made me appreciate how amazing Scala's compiler is and the cool things you can do with it. Additionally, there's lots of things in the ecosystem that use this technique, so it's super cool. So let's talk about what we're going to do today. We're going to make sure everyone's on the same page with what induction is. Then we're going to make sure everyone's on the same page with what a type class is. So I'm going to assume nothing. So some of you wizards out there and witches are going to be super advanced, but bear with me. I hope there's enough jokes to tie you through. Then we're going to do our baby's first type class induction. And then we're really going to shift the gears of abstraction. And then, you'll all become logicians, which means the new part of this talk will be, I'm going to show you how you can apply this to define servers and generate clients and servers for them. So that's going to be our agenda today. So let's get started because we don't have much time. I really got to hurry. So let's talk about induction. Usually when I want to explain induction to somebody, I want to talk about Domino's, but not Domino's pizza, this kind of Domino's. And basically, you can use induction to prove properties that are true for many things. So for example, if I have a bunch of dominoes and I want to prove that they fall and I want to do this inductively, I do this in 2 steps. So most inductive proofs have 2 steps. The first step will be a base case. And this base case basically proves the property for one of your things. So if I want to prove that all my dominoes are going to fall, I need to first prove that one can fall. So then basically I can prove that you can knock over one. You all have fingers, so you can knock over one domino. Secondly, the second part of an inductive proof is what's called the inductive step. And in this step, basically what you want to assume that your property is true for one of your entities and prove that if it's true for this entity, it will be true for the next entity. So in the case of the domino thing, you want to say that, hey, if you give me any random domino and it falls, I will prove to you that the next one will also fall. And the way you would do this if you had dominoes is you just measure the distance between each of your dominoes and say, well, all the distances are less than some triangle thing, and so therefore they'll all fall. But note that you need both of these properties to prove that the dominoes will fall. If you don't have the base case, but all of your dominoes are close to each other, they're still close to each other, but none of them are falling, so they're just going to be stationary. If you only have the base case, but not the induction step, you'll knock over a domino. Maybe some other ones will fall, but eventually you'll get a gap that's too big, and they all will not fall. So you really need both these cases. So that's induction. Now, you've probably encountered induction in programming, maybe called structural recursion, but I'm a mathematician, so I prefer this term induction. But let's just give some examples to get your mind trained because we're going to do a lot of these things. So you can give an induction definition for the length of a list. I don't suggest you do this in production, but it looks like as follows. You first take your base case. What is the length of an empty list? It is 0. Then you do your induction step. If I know how to calculate the length of a tail, then I can tell you what the length of a head const onto the tail. And this will give you the length of a list. I hope you all agree. You can also do the same kind of thing if you wanted to give an inductive definition for mapping over a list. Okay, give your base case. Well, I know how to map over nil. I just return nil. But if I assume that I know how to map over the tail, then I can prove to you that I can map over the head const the tail by applying the function to the head, consing it to the result of mapping the function over the tail. So again, this whole idea of showing something for the base case and then doing an induction step is, if you've done structural recursion, you're familiar with this, but this is basically the logician's form of induction, and we're going to do this over and over again. So I hope you are all really cool fans of induction, and now we can move on to type classes. All right, so who has a good definition of a type class? I hope none of your hands get raised. I really tried to find a good definition of a type class, including reading Philip Wadler's original paper, including a lot of Wikipedia digging. That's my definition of good. There does not exist a good one. So I'm just going to give you my definition, and y'all will bike shed me to death at the end of this, but my definition of a type class, and I think it's a good one for pragmatic use cases, is that a type class associates functionality with a type. Now, so you can think about it like a mental model where here's a type class called foo, parameterized over a type A. It associates behavior foo with A. Now what that functionality or behavior is up to the type class, but that's the kind of mental model we'll go with. So if you're not familiar with type classes, you can keep this in your mind and we'll go through some examples. If you are familiar with type classes, we can have this debate another time. What's cool about type classes is that you can rely on implicit resolution to find and use type class instances. So the Scala compiler will actually do work for you to find type classes and then use them. And you pay a lot of time to like compile Scala code. It takes a long time to compile Scala code, so it really should be doing work for you. And this is how you get it to do work for you. So make your compiler work for you. So as an example usage of a type class, I might have a function called bar parameterized over a type A. I don't know what A is, but what I can assume, instead of like assuming that A is in some subtyping hierarchy or some inheritance hierarchy, I can just say, hey Scala, I have an A. I really want the functionality that comes with foo for this type A, so give it to me, and it'll find this implicit if it exists. And this is kind of how you can use type classes, and they're super cool. And again, you'll get more examples in a second. So let's give an example. Functional programmers really love this particular type class. It's called squishy. It's parameterized over a type A. And what it does is it takes two A's and squishes them together to produce an A. All right, this is a really popular type class in most functional programming. So, an example of how you might use the squishy type class is you might say, I want to take any A that's squishable and just squish it with itself. So to write this kind of function, I just take an A, but then I say, Scala, find me an implicit instance of the squishy A type class. And if it can find that, it'll just squish the A to itself. So that's an example of a type class and how I would use it at a call site. Now, you might say, do any squishy things exist? And I will give you an instance. Here's our type class. An instance. Integers can be squished. I can just add integers together. All right, so this is a cool type class, and it's really common in functional programming. But what's really cool about type classes is not just that you can have an implicit value or instance of it, it's that they're like truly a little bit magical. So for example, again, just to remind you, here's our type class. Now, imagine you know how to squish an A. Theoretically, you should probably know how to squish an option A just by using the A squish, Like basically, if I know how to squish two things, then if I have a sum of one of the things and a sum of another thing, I squish them. But if any of them are missing, I just return nothing, right? And Scala will actually produce this code for you. You can use what's called an implicit definition and basically say, hey, if I have a squishy A, Scala, produce for me a squishy of option A. So if we have squishy A, Scala, give me a squishy of option A. And it will do this, at compile time, in line where your definition is. But, exactly this, to implement this, it's exactly what you would expect. If you have an option of A and an option of the other A, you grab the options, you squish them with the squishy A instance, and now you have a way to squish option A's. And this is really cool because all of a sudden, our type class resolution has become a sort of like primitive logic. This is sort of like logical implication. If I have an A, then if I have a squishy A, then produce a squishy of option A. And, once you give a functional programmer a little bit of implication, they're going to take a lot of induction. And that's what we're going to do right next. So the question that might come to somebody's mind is, can we leverage this implicit resolution to do induction when we're resolving our type classes? And the answer is yes. So here's what we're going to do. This is the bread and butter of the talk. Okay. First, we need a thing to do type class induction over. So we're going to define a type level list. There's way better ways of doing this, but for simplicity, it's going to look like embedded tuples, and I'll tell you all about it in a second. Second, we're going to define a type class, something that associates with each type a name. And we're just going to use this type class to do a dummy instance so you can get kind of the mental model of how things are working. And what we're then going to do is show you that I can derive a named instance for any type level list. And that will be where the magic happens. And we're going to do this by showing you an instance for a base case, and then as an induction step saying, hey, if I have a named head and a named tail, I'm going to produce a named for the tuple head and tail. And that's going to be our induction step. And then we're going to take that to the next level, but just give it a second. Okay, so type level lists. Like any list, you need a nil element. So for our type level list, we're going to just use unit. Okay, it's just an arbitrary choice. It could have been any type, but I picked unit. Then we're going to encode a list as basically a tuple, where you have a head in the left part of the tuple and then the tail of the list in the right part of the tuple. And this structure lets us do induction, where this is our base case and this becomes our induction step. Okay? Y'all with me so far? You see how this can be a list? It can be arbitrarily long and it'll always terminate in a nil. You could actually make normal lists like this. They would be terrible for memory. Well, maybe not that bad for memory, but maybe the same as normal lists. Anyways, the point is we just need a representation for type level lists. So the next thing, part 2, we defined type level lists. We're going to need a type class to do induction with. So here's our name type class. Like I said, it associates with each type a name. So for example, we have an instance for integer where we just have the string int. An instance for char, we just have the string char. Can anybody tell me what the instance for string will be? It has a name string. Okay, just making sure you're all awake. I see some sleepers over here. That's right. So now we have some named instances for our name type class, okay? So now we're going to do the induction, okay? The moment you have all been waiting for. All right, so here's our type class. One quick little interjection. Who can guess what happens when I do this? I heard a weak char. Char, yes, you will get char, okay? So that is implicit resolution happening for our name type class. Okay, we're going to use this little trick of going to my fake Scala REPL and conjuring stuff in a second. Okay, so let's do induction now with named. The goal is the following. So this is our goal. We haven't done this work yet. The goal is to get a named instance for any type level list. So what will this look like? If I call implicitly on this type level list, int char string, what do you think I want to get out of that? Actually, you won't know the answer to this. I'll just tell you. I'm going to get a list like int char string. Okay? Concatenate all the names with some commas. So that's our goal. And this should seem pretty magical to you, but there will be some slides that will explain what's going on with a lot of emojis, and you will understand. Okay, so let's start. So like any good inductive proof or definition or whatever, we start with the base case. So when we want to find a type class for a base case, we basically want to produce a type class for our EOL type, remember, which was unit. So our named EOL is just going to have the empty string. We're done. That is the base case for our named type class. And now, here's where the magic will happen. Our induction step. Okay, so we've got our named E. And now what we have is something interesting. We have an implicit definition. And what this definition says is that if I have a named head, and if I have a named tail, then I will produce a named for the tuple of head and tail. And how do we do this? Well, we new named head and tail, and we give it the name where we use the named head instance and the named tail instance to concatenate the strings, and then we're done. So again, that was our inductive set. I know I have a named tail. I make an additional assumption that my head is named. And if I have those two things, I can produce a tuple of named, or a named instance for the tuple head and tail by just concatenating the strings. Okay? And this is all I need to do. If you now call this, you get something slightly different than what we wanted. You get a trailing comma. But nonetheless, it's doing the thing. Further, if I then call this on a huge type level list, so I have int char string int char char char, what do you think we should get? Int char string int char 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 comma trailing space. And this is all happening at compile time. So I didn't have to write any of this code. I can make this arbitrarily long. We just all day long, huge list, put Scala to work, give me a string. Imagine you had a business. Imagine somebody wanted to buy these strings. You don't have to do any work, no employees, okay? Pure business. So the question that came to my mind when I saw this magic happening was, what is happening? How does Scala do this? You know, this is me at work every day wondering, how does anything work, okay? So let's get a little deep dive. So we called this. We said, the witches of Scala conjure for me a named instance for int, char, string, EOL. So what Scala will do is it'll say like, okay, let's look for exactly the named instance of this. Did somebody lazily just write the named instance for this? And of course it will not find it. And then it'll say like, well, what do I know? I know that I have a named instance for integers, right? And I know that if I have a named instance for integers and a named instance for the rest of that stuff, then I have this implicit definition that says if you have a named instance for the head and you have a named instance for the tail, you can produce a named instance for the tuple of the head and tail. So it'll say, I found the named instance for the integer. Do I have a named instance for this tail part? And it'll go, okay, do I have a named instance for char, string, EOL? And it'll say like, no. But I have that implicit definition that says, if I have an instance for the char and I have an instance for the tail, then I can produce a named instance for the head and the tail. And it'll say, okay, do I have a named instance for string and EOL? And it'll be like, do I have this? No, I don't have that. But I have this implicit method that says, if I have a named instance for the head and a named instance for the tail, I can produce a named instance for the tuple of head and tail. And in this case, it says, hey, I totally have a named string, and I totally have a named EOL. The named EOL was our base case. And then it rolls all that up and returns for you this instance, doing all of that work for you. So that is how, when you call this, it'll traverse and produce this beautiful string. So does anyone have any questions so far? Is this clear? Yes. I heard a yes. Oh, you have a question? Yes, I would love to. Soak it in. So right here you can see, here are my assumptions, right? You have to say, Scala, find for me a named head and a named tail. If you can find those, this implicit method will produce a named instance for the tuple head and tail. Okay, take a photo. Keep it in the mind, because we're really going to shift the gears of abstraction quite a lot, okay? But first I have to get to an aptly named slide. What have we done? So let's just give a quick recap. We defined what a type level list was. Just these embedded tuples, okay? Int, char, string, EOL, okay? Then we defined this type class name that associates with each type a named string. And then we were able to derive a named instance for any type level list, so long as they consisted of the instances we have of named int, char, and string, and EOL. And we did this by giving a base case for named EOL, and our induction step where we assumed that we have a named head and a named tail, and we're able to produce a named for the tuple of head and tail. And then we called this and showed that it conjured the right string. So now I want to really press the accelerator on the engine, okay? In German, you might say macht schnell. That's about the extent of my German. I'm really trying hard, though, to learn. But we're gonna do this, okay? So let's go back to our problem. The problem was we have this heterogeneous event sink, okay? The data lake, that's where the business value is accruing, but somebody's got to maintain that event sink. They're adding events is horrible. And we had to do this dynamic dispatching, and we want to get rid of that. So what we're going to do is we're going to create a new type class called dynamic dispatch, and it's going to be parameterized on our list of events. But we're going to throw a little cool thing. Did anybody see Nada's talk on Dati? It was a lot about these path-dependent types. We're going to have a path-dependent type here, which is called out. And this out represents what is the final result type of doing a dynamic dispatch, which is like either a click or a pause or a play or nothing at all. And then this type class is going to have a method called dispatch, which just takes the name of an event, the payload of an event, and returns an option of out. So whatever the out is of this type class will return an option of that. And the reason for this path-dependent type is that if I have like 10 events, the result of trying to parse one of these events is going to be either click or pause or play. Inevitably, the result type is going to be depending on how big the stack is. So we need to actually produce it dynamically. I think it'll make a little bit of sense in a second, but don't let that trip you up too much. So I'm also going to assume there's some kind of like parsing type class. This is just for convenience and show you how you might use this in the real world. And it just takes strings and turns them into option A. So this is your JSON parser. You know, Circe is the one I recommend. I don't profit from that endorsement, but the people who wrote it are nice. Okay, so let's do this. Remember, the first step of any great induction proof is the base case. So here's our type class. The base case for our dynamic dispatch is basically we can't return anything. We have exhausted the list of possible things that we're going to try to dispatch on. So our output type is nothing, and our dispatch returns none. And in fact, this is the only instance for this type class that you could write. If you had to show up at a job interview and they're like, okay, you reversed the tree on the whiteboard, now provide to me the base case instance for this dynamic dispatch case. This is knowing nothing else, this is the only instance you could write. It returns nothing and it just returns none. Okay, so that's our base case. Now let's go to the inductive step. Reminder of what the type class is. Okay, so our inductive step. Our inductive step assumes that the head of our list is named, that the head of our list has a parser. So these are just some assumptions. And if those things are true, and I can dynamically dispatch on the tail, then I will produce for you a dynamic dispatcher for the tuple of head and tail. Okay, so we need to produce an output type. And the idea here is that we're looking at a type like click, and we have a named click. And so when we're going to try to parse a click, either the name click is going to be present, and then we'll parse the payload, or it's going to be the wrong click. So either we're going to return you whatever this head type is, or we're going to try to go down on the tail. So that's why the output type here is either the tail instance out or whatever the head is. And basically our dispatch is going to take the name and the message and return it out. And our dispatch function is going to be pretty straightforward. It's just going to say, if the name that is passed into dispatch, so if someone says parse this click, if that is the same as the name of the head, then try to parse it. And then map the result to write so that we can get this option out. I mean, there's a lot of like finickiness in here, but I think when you see how it works, it'll start to be a little bit clear. Otherwise, just try to dispatch on the tail. So this is doing exactly like, this is just doing exactly like, is click equal to pause? If it is, try to parse it. Otherwise, go further. But note that going further, we don't know how many more things to dispatch against, and that's why we have to use this path-dependent type. So let's see this in action, okay? So remember, suppose I implicitly required us to have this dynamic dispatcher, and I get this result 10. If I then try to dispatch, where I pass it the string integer and a payload of 10, so these are my like little events, if you will, I get some write out. Now remember, if you see the output of the dispatch, it is option of out. So we see that you get an option of whatever out is. And in this case, it's a write. But who can guess what the output of this will be? So I'll give you a hint. It starts with some, because it's got to be an option. Yeah, it's not an int, so it's a left. Whoa, some of you are falling on. I'm barely following along back here. Did it not show? Oh yeah, there you go. Oh, it had the answer on the slide. I'm sorry. See, I told you I wasn't following along. Okay, yeah, so as you can see, you get some left, right. And further, if you try to dispatch on the string, you get some left, right, whatever that string was. Because remember that the output type, we had to like recurse into our either structure depending on how we're dispatching. And if you just put in Scala world, you get none. But don't worry, it's a great conference. So what we've done is basically dynamic dispatch, but statically in some kind of weird way. And it did this all at compile time. And what's really cool is I can keep adding like events to my type level list, and so long as they're nameable and parsable, I'll get my dynamic dispatching for free. And so you might wonder, like, like I said in the beginning, you may or may not want to do this in your code, but there's a lot you can do this. So for example, you can think about like some kind of generic deriving. So if I can take my case class and transform it into a type level list, then I can just do type class induction and generate type classes for anything that's a case class. And this isn't exactly what they do in Shapeless or Circe or other libraries, but spiritually, it's very close. And what I really want to show you is like what's really cool. And that's, can I use this method to describe HTTP servers and then generate things that if I supply them with the right functions, give me HTTP servers? Because if I show you this HTTP route where I say like the first part of the route is add 10, then get a char out of the path, then get an integer out of the path and return a string, like that's kind of how I tend to think about HTTP servers. I have some root, and the roots are always like simple functions. But the problem is that you have all this ceremony of like pattern matching on roots and, I don't know, scaffolding your server and stuff, when really you just want to say like, hey, I'll give you the function that if I have a char and int and returns a string, I can do that. That's the easy thing. The rest of that junk, that is just ceremony. And what I can say is that you could do this. And my inspiration for doing this came from a library in Haskell called Servant that I worked on a little bit, and I got the sneaking suspicion that, hey, I could probably use the same type class kind of methods in that library and apply them to Scala. And so a little special treat for this crowd only, I will show you exactly that. So this is where things are going to get a little bit weird and wild, but, error. Here we go. Okay, so I'm not, I can show you the code is horrible mess of stuff, but basically, here's my route. So I'm running my HTTP service. I gotta write a route that adds 10 to numbers that sends it in. Okay. So I'm going to describe this with a type. Okay. So I'm going to say that the path, it takes a path of add 10, and then it'll capture a char from the root, and it'll capture an integer from the root, and it'll return an integer. And the idea on any GET request. And the idea is that I can look at this and I know that all I need to do is provide that function that takes a char and an integer and returns an integer, right? Like, logically speaking, that's really what the core of my business logic is that function. Okay. Similarly, I might have a route that's called cool, and it will just add cool to anything you pass in. And really, I just need to write that business logic that takes a string and returns a string and adds cool to it. I don't want to have to worry about any of the ceremony. Okay. And what I can say to you is that this is possible. So basically, I compose, so I have these types, I then compose both roots into a type, and I say, conjure me the instance for this server, okay? Now, what is this instance? This instance is something that if I give handlers to, it'll produce a server, right? So basically, we have, sorry, I'm totally zipping through this, but we have our server here, and if I give our server 2 handlers, it'll give me an HTTP service. So here are the 2 functions I was talking about. Here's my function that for this route, where it just takes a char and an integer and adds 10 to it. It's just a function from char to integer to, it's not exactly integer, but it's like an either t integer. You can see here it's returning I plus 10. Similarly, my cool route takes a string and returns a string, which is, again, the core business logic of your server. So I've defined these roots at the type. I've specified their structure at the type. And then I wrote these functions that have my core business logic. And then I just, I start up my server right here. Okay. And now let's see what happens. So I'm going to run my thing. And I'm going to call this, right? So remember, this was the root. Oops. Let's go up. This was this root, right? Add 10, expects a char, expects an integer. Okay? And I'll get back 20. And if I fuck this up and I don't put a char here, I get back a 401. Okay? Whereas before, just to make things complete, I got, oh my god, whatever. Okay, and for the other root, which was the cool root, let's put you, the audience. It says you, the audience, is cool. And if I put something else in here like coolio, it'll not recognize it. And really all I did was write these functions, was define this API at the type, write these functions, and then give them here. This is just some bullshit to deal with finagle. And put it in here, and my HTTP service is done. I didn't have to do any parsing of roots, none of that shit, matching. Who wants to match a root? Not me. Like all of that was handled by doing type class induction on that structure and generating a thing. Now it's a little bit complicated, but you do that once and then you get this. And what's really cool is that this specification, right? This specification of my HTTP root at the type level, I interpreted it to produce a HTTP server. I could equally interpret that structure and produce an HTTP client where you give it an integer, you give it a character, and it returns to you a string, generating all the client bindings, making the call to the server, marshalling stuff, and returning it back. You could also interpret that structure to produce documentation. You could also interpret that structure to produce mocking, etc. All of this by just doing the type class induction. You have one specification and multiple outputs. You don't need to interpret a free monad AST. You don't need to worry about monad transformer library. You just need to make sure that your work is I/O bound because you're going to have a lot of dynamic dispatching. So let's go back to here. So in closing, to do type class induction, you need some kind of structure, either some kind of type level list, or in the case of that server stuff, some kind of structure. And then you need really cool type classes to interpret that structure. And you have to do it first in your base case, and then making some assumption on the head and the tail, produce an instance for the tuple of your head and your tail. And now you're a logician who's leveraging type class induction. Thanks so much. We have like 5 minutes for questions, if anyone has any. We got a hand up over there. Yeah. Yes.
So first question is, because you haven't shown the case where you clean up some of the output of the named vista resolution.
Yeah.
Am I right in saying that all you have to do is to introduce another method that just has a head unit parameter?
No, even simpler instance. So the question was, when we did our named instance here, we had this trailing comma. This is your question, right? How do I get rid of this? So really, really simple solution. So your solution may also work. So I'm not going to negate that solution. I think your intuition is in the right direction, but there's a simpler solution. Basically, the named type class here, if instead of a name value, if you just had a def that carried through the strings, then in your base case, you could clean it up. I didn't want to do that because it takes away from the simplicity of the example. So you don't need to do anything fancy to clean that up. You just change name from a def, and it'll take like an accumulator, and then at the base case, you take the accumulator, you clean it up, and then also in the induction step, instead of just inlining them with a comma, you accumulate and pass to the accumulator in the tail instance. You might have to reverse them too, but basically it's like the same kind of recursive technique. Yeah. So you don't need anything fancy, yeah. Cool. Your question below.
Do you plan on open sourcing these HTTP VSF?
I would love to have the time to. So I did this in just the other day in preparation for this talk. There is a lot of nasty error handling and stuff that needs to get this ready. And like I worked in the Haskell. Okay, so the question was, can I open source this type class wizardry? And like I'm not against that, but it's going to take some while to get it to like a usable state that's not doing some intermediate inefficiencies and other stuff. If you want to see what I can do is I can put that horrible code online, and so long as you don't shame me for like ugly parts in there, then I'm happy to let the world get inspired. Yeah, and it's probably a little bit. There's a lot of in these instances we are either like constructing a string or inductively constructing an output type. In this instance, it's a little bit more complicated because you're like inductively constructing a function signature that you're going to ask somebody to supply for you. So probably if you went and looked at the code, you'd be like, whoa, what is going on? But like it's holistically kind of the same. Anyways, I don't know why I'm ranting about that. We can talk after. I'll try to get it up on in here. I'll try to get that code up like soon. Does anyone else have any questions? We had a little bit of a tail or a mutual recursive thing over here. Did you get all your questions answered? Okay, so the question is, why do you need the path-dependent type in our type class? So here's our dynamic dispatch type class. Why do you need the out? So here's the question of you. This type of recursion, I don't know. So the question was, if instead of having a path-dependent type out here, can we maybe have a parameter on dynamic dispatch that holds that information? The problem is we need to modify that type as we go through the structure. So my real answer to you is like, I don't know. I don't think so. And the problem is that you need to recurse through the structure. If there's a way that I can like grab something below me in my induction and stick it into the generic parameter of this type, then yes. But I don't know if that's possible. Yeah. So like one thing I can say is like, here's the exercise. Remember that this list of events is unbounded. It could be super long. And I need to return something. So like before we even do the induction, think about this method, dispatch. What does it return? It returns option. It can't return option of integer because you may return a click. It can't return option of string, comma, integer. You got to put something there. And the problem with this something is that what's below you in the induction is unknown. That could be 500 types. I think that's an interesting intuition. But let's talk about this after because we got to let the next speaker come up. Okay? Thanks, everyone.